Welcome to this video produced as part of the Further Maths Support Programme's supporting material for A-Level Maths and Further Maths. This one focuses on the basic principles of mechanics and in particular on quantities in mechanics. To begin with, we need to be clear about the three fundamental concepts in physics, that of mass, distance and time, that we're going to use in mechanics. Mass has a unit of kilogram, that's what we agree to use, and distance has a unit meter and time second. There are other possibilities. For example, if the context involves very small quantities of mass, we may choose instead to use the gram. If the distances involved are large, we may choose to use the kilometer, and if the time is long, we may choose to use hours. In each case, that's determined by the concept, but we must agree fundamentally that we're relating to those three concepts, those three units, kilogram, meter and second, and any other units used will be defined usually in terms of those. Then we must consider the difference between scalar and vector quantities. Scalar quantities are obviously the easiest to use since they only involve numbers. When you go into vectors, you must consider direction as well, and that means that either we've got to specify the direction, as in north, south, east or west or some other means, or we have to use a number of dimensions or components. That will become clear later. Scalar quantities have only magnitudes, whereas vector quantities have direction as well. Here are two examples of scalar quantities. Speed. A car has speed regardless of which direction it's travelling, and similarly a pedometer will give you distance even if you walked around in a circle and come back to where you started from, and distance is regardless of direction. In each case there is a vector analogue, and that is, for speed, its velocity, where you must specify speed as the magnitude of the velocity and its direction as well. And similarly, for this distance, there's displacement, where you specify not just distance, but the direction in which motion has taken place. Here we have a brief word about vectors, and in particular a focus on one idea of vectors as related to force. The third paragraph on this slide refers to the idea of acceleration downwards and to gravity, which is a force. Acceleration is downwards in the direction of the centre of the Earth, even if at a particular time the object in question has a velocity which tells you that it's going upwards or some other direction. Similarly, the pull of gravity is always downwards towards the centre of the Earth on the Newtonian model. Again, you can consider a tug of war where you've got perhaps an equilibrium, neither side's winning. You've got two forces, and the whole point is that they're in opposite directions. So again, you have the fundamental idea of vectors, that despite two groups of people exerting huge force, the end result is zero. Now let's look at the context that we use. In any particular context, it's important to decide how you're going to describe it. Sometimes it would be appropriate to use scalars and sometimes it would be appropriate to use vectors, but it needs to be clear at the outset. And here's an example of how that difference could pan out. If you want to talk about moving backwards 5 meters, you can say it in two different ways. The displacement is negative 5 meters if you take forwards as defined as positive, but on the other hand the object has moved a distance of 5 meters backwards. So long as it's thought out at the beginning, it should be clear what to do. Now let's look at this graph. It purportedly talks about some fictional person called Jane, who's walking 160 meters from a starting point to a bus stop on a straight road. That makes it apparently very simple, until you look at the graph, when it seems to become complicated. If you look at the first section of the graph, you'll see that our friend Jane has walked a distance of 100 meters from the zero line up to 100 meters, and a time taken is 50 seconds. So in this situation we can see that as the distance is increasing, as time increases, she's walking away from the starting point, and that by implication is in the direction of the bus stop. But if you look at the second section of graph, over that line her distance from the starting point is reduced from 100 to 40. That must mean she's walking in the opposite direction as time increases. Perhaps she dropped a bus ticket and has had to turn around and go back for it. And then, after 70 seconds have elapsed, she resumes walking in the same direction, but since we notice that that line is steeper than the first one, it will correspond to a greater distance in the same time. 30 seconds on that second section of graph, she covers 120 meters, whereas on the first section of graph, in 30 seconds, she's only reached a distance from the starting point of 60 meters. So the steeper graph indicates that she's travelling faster. Well, the question on the slide is there a problem? Only if we have thought of some way of explaining what's going on. Now let's look at a description of this in terms of numbers. First of all, look at ideas of speed. On the first 50 seconds, that's the first section of graph, the speed is 2 meters per second because she travels 100 meters in 50 seconds. Similarly, the velocity is 2 meters per second away from her starting point in the direction of the bus stop. If we think in terms of distances, then she travels 100 meters away, and then she comes back 60 meters as we discussed, and then finally a last 120 meters rather faster to pick up time, make up time. So we can see that the displacement is different from the distance. In the distance you have the 100, the 60, 120 added together giving you 280, and for the displacement you've got to make the 60 negative, and so the final displacement telling you where she is 160 meters away from her starting point. Now let's look at some kinematic terminology. Here we're faced with a more complex situation involving a car and a motorbike. The two graphs are labelled so we can see which is which. The curve is the motorbike and the car is denoted by the line. Now the line starts 10 meters displaced from the starting point, so we must assume that they don't start at the same place. While the car proceeds in what is represented by this straight line, we'll see, and it's be spelled out in a moment, that at each second the car accomplishes a further displacement of 10 meters. That means it's travelling at a constant speed, whereas in the case of the motorbike, because the graph is curved, it's not travelling at a constant speed. And this point where the two graphs cross indicates where at the same time they're at the same displacement, so they must be passing. And since this line indicates that for a particular time the displacement of the bike is always less than the displacement of the car, at that stage the bike is chasing the car. But where the graphs cross, we see that thereafter the motorbike has passed the car and is travelling ahead of it. Now let's look in detail at the car. I've already indicated that you're getting an increase in 10 meters for every second, which tells us that it's got a velocity of 10 meters per second. Let's look now at the motorbike. Interestingly, here with these markings on the graph, you can see that in each successive second it's travelling further and further than the previous one, and at every time it's travelling 5 meters further. So we can see that if we look at average speeds, for the first section you've got 5 meters per second, the second 10 meters per second, the third 15 meters per second, and so on. So in each speed, we can see each second the speed increases by 5 meters per second, which means that what we've got is an acceleration of 5 meters per second squared. So we could add that in as an annotation, that we've got an increase in speed of 5 meters per second, so that's 5 meters per second per second. That would mean 5 meters per second, s to the minus 1, that is, s to the minus 1, and we'd write that as 5 meters per second squared, s to the minus 2. That ends this first video presentation. The next in the same series on basic principles of mechanics focuses on modelling. I hope to be with you later to explore that.